In this class, what I am planning to do is to take some examples of how an experimental study has been carried out to understand deformation behavior of some systems. Okay. What are things which are required to do it? Because one is when you do a modeling, we look at a specific mechanism. But when we deform a sample and look at it, whatever possible mechanisms which can operate, all the mechanisms will be there. Okay. So this is what I will try to tell, how one has to go about to understand the basic. So if you wanted to do a study, what's the first thing which one should require? One should know about the material which we are going to study, right? If I say that you work on a stainless steel, the first question which you will ask is that what is the type of steel? What is the crystal structure the material has got? Correct? That information is required. If that crystal structure you know, what are the types of dislocations which it can happen, then you will ask that question whether it's a high striking fault energy material or a low striking fault energy material. Okay. Depending upon that, the dislocations might have split into partials. Okay. Then knowing the crystal structure, it need not always be BCC and FCC or HCP structures. It could be some ordered structures. Then you should first experimentally try to find out, okay, what all types of dislocations are there. Okay. What is the crystal structure? It can so happen that material some second phase precipitation occurs. Okay. Even before you study the deformation, you should know what is the type of precipitate which is there. Okay. Depending upon the type of precipitate, how dislocations are going to interact with that precipitate. Okay. That's what is going to decide the strength. Okay. This as a case study which we have done over decades on Inconel 709, which I will present it to you. Okay. So when you had looked at the precipitation behavior of this alloy, okay, what you had found is that there are three types of precipitates which form. Okay, in this alloy, this is a nickel-based superalloy in which a gamma prime forms. Gamma prime has got a crystal structure similar to that of an FCC, except that it's an ordered system. Correct? Okay, this is one. And in this, when we have to look at the deformation, if it's an FCC type of system, what one has to look at an ordered structure? Look at how the arrangement of atoms are there in the closed packed plane. Correct? So that is why I had just shown the closed packed plane, which is 1-on-1 plane in FCC. Okay. In this, if you see, what is the difference between FCC and here? Only thing is that these particular positions, it's a different type of an atom which is occupying. If you forget about that, it's essentially like an FCC 1-on-1 plane. Correct? And another structure which it forms is gamma double prime. This is the main strengthening phase in this alloy. Okay. In fact, this is a metastable phase which doesn't form in binary system nickel 3 niobium. Essentially, its composition is nickel 3 niobium with part of niobium replaced by aluminium and titanium. Okay. And it is something similar to keeping one of this structure again on top of the other. Okay. And then introducing an antiphase boundary. Antiphase boundary means that you make this atom come here, this atom move to this side, like a slip which is being created. If that is given, this sort of a structure will come. This structure, if we look at the closed packed plane, it's again also like an FCC structure. Only thing is that now the atoms which are minority atoms which are occupying the positions on the plane, they are slightly different. Right? Here, if you see, you have a threefold symmetry is still present along 1-on-1. Here, if you see, the threefold symmetry is lost. Okay. I will come to this structure and explain. And this phase forms at temperatures from maybe 400 to 900 degrees centigrade. Okay. And above 900, okay, up to 1000, it's essentially the equilibrium phase which it forms. Equilibrium phase has got a orthorhombic structure. This alloy is a very complicated alloy, but this is used in many of the aircraft engines as turbine, high pressure turbine blades, vanes, so many, that's many engines, it's about 40 to 60% by weight, the single alloy is used in most of the aircraft engines. So it's a very important alloy. Okay, and this is used in nuclear industry. That's how we are interested in studying this. Okay, here also, if you look at this one and this structure, if I disordered it, it is nothing but an HCP structure. Okay, so the equilibrium phase has got an HCP lattice which is ordered, and if you look at the closed packed plane, this is essentially also all of them have a same type of a closed one-on-one type of a closed packed plane, and especially here and here, if you look at it, the arrangement of atoms are the same. Okay, but here the stacking sequence is like ABC, ABC it comes, but I will explain how this A1, B1, C1 it is given, because there is a slight difference is there, and here it is nothing but an AB, AB. So by introducing a stacking fault in FCC, we know that HCP structure can be created. Same way, if you introduce a stacking fault in an ordered alloy, we will be creating a nuclei of a structure which is HCP ordered. That's what essentially happens in this alloy system. Okay, is it clear? When this alloy is aged, okay, at temperatures to give the maximum strength to it, okay, this is the sort of precipitates which form, which are essentially ellipsoidal in shape, okay, which are gamma double plane, which is the tetragonal structure, and there are some spherical particles are also there, very small ones which you can see it. They are called as gamma prime. These two phases, what I had shown the crystal structures, both of them are formed in this alloy system. Okay, and in fact, since it is a tetragonal phase, if it forms, okay, in an FCC, if a tetragonal phase forms, what are the different orientation variants which it can have? Lattice parameters are almost identical. Then what it will happen? Essentially, three variants can come. That is, this is a tetragonal structure. Okay, if it forms in a FCC cell A, B, C, okay, then with the C axis, this is A, B and C. With the C axis, along the C axis of the FCC, it can form one possibility. Another is C axis along the A axis, it can form. That is, this will be as if it is lying like this in this one with C axis. Otherwise, it can form with the C axis on this. Because since it is tetragonal, these phases we will be able to see distinguish them separately. That is what essentially what you are seeing them, and they have an ellipsoidal shape. That is, when an ellipse is there, it's just, okay, it's like a circular one. This is nothing but the hammer throw, what we use that. Okay, that's the one. That shape, if you look from the top, it will look like a circle. If you look from the side, it will look like a ellipsoidal shape. That is precisely what we are seeing, because this is nothing but a projection of that particle size morphology. That is what you are seeing it. And using these superlattice reflections which are there, using them, they have been imaged and identified. Okay, this is how we have to do it. I am not going into how exactly all these things are done. Okay, that's not the focus of this talk. So, but I just want you to understand that using superlattice reflections, we can image the precipitates. The same precipitates I showed in bright field in an earlier class, where it has a, because this has a coherency strain associated with it. Because of the coherency strain, we cannot see the boundary of the particle properly. Whereas in this, when we image them in dark field, we can see the precipitates very sharp clearly. This is how it has to be imaged to find out the particle sizes. Okay. As this precipitate grows to a large size, you can see that there are some faults which are forming, because these precipitates have got a low striking fault energy. Okay, like an FCC is low striking fault energy, in the ordered one also striking fault energy is low. When the striking fault energy is low, they form faults, and this fault is nothing but nuclei of the HCP ordered phase to form. So they form from this. Okay, and this is how how the stacking sequence changes, that is being shown for an FCC. Here also the same thing which is being done. If you look at it, this is a layer, then the B layer atom will be moved from here to here by A by 6112. That's a partial which creates stacking fault in FCC. Okay. Then the next atom, if we consider, which is on a position which will come here. Okay. From here it is moved to this position. The next atom, when we consider it, it should have been the stacking sequence. It should have been like a atom which represented by open circle. That's nothing but here it will be a nickel atom. Instead, the closed circle is being put because niobium atom. That essentially, that is why we have a stacking sequence which is a 6-layer stacking sequence, like in BCC. BCC structure, if you look at it, you will have a 6-layer stacking sequence along 1 and 2 direction. Okay, because this is a body centered tetragonal. So many of them, by crystallographically, also if you look at it, the stacking sequences and all these things are fixed. If you have to work out as an assignment, then you will understand how it happens. Okay. So these faults are the one which essentially, when we age at high temperature or when we age for a prolonged period of time, okay, this equilibrium phase forms, consuming the metastable other phases are there. That is, if the alloy, when we age it initially at some particular temperature, we find that it has some particular strength. As you age it for a long time and then look at the yield strength, it comes down. That is because it might have completely transformed to the equilibrium phase. When the equilibrium phase it has transformed, the interparticle spacing is very large, then the strength also automatically comes down. You know that the strength is related to interparticle spacing. Okay. So this, in a nutshell, I have just described what are the types of phases which it can form, how from one phase it transforms to another during heat treatment. Okay. This sample has been given different heat treatments, okay, and then we try to find out, done a tensile testing, okay, for different periods of time. These are all the particle sizes which are there. At room temperature, try to find out what is the yield strength of the material. You can see that the yield strength of solution treated alloy, which does not contain any precipitates, around 280 megapascal, and as the particle size increases, you can see that the strength increases, okay, yield strength, and then beyond a particular one the strength starts dropping down. Okay. And how do I identify a particular type of a mechanism which is occurring in the material from a stress strain plot? The change, that's work hardening rate. If you look at it, how, so that is essentially what has been done, that Ludwig plot, it has been trying to plot it and then try to find out what is the value of n. Here if you now work hardening coefficient. Okay. Now you can see that for the solution treated and the one where the precipitates could not be seen, it has a very large value. Okay. I could not locate that plot, otherwise I would have shown that. Okay, anyway, this table I could get it, and you see that when beyond a particular particle size, this work hardening coefficient has dropped down. That means that compared to solution treated sample, the mechanism by which the dislocations are interacting, there is a change is there, correct? This is what essentially which one can conclude, the mechanism of deformation is different from this plot. Okay, once we have got this, now if we wanted to analyze it, the first thing which we should understand is, we know what is the crystal structure of the precipitate, what all types of dislocations can be present there, okay, how they will be generated, okay, how they can contribute to strength. That is the information which we require first. How these precipitate dislocations will interact with the precipitates, that is the information which we look for, right? That is as a natural consequence. So here again I had just shown the closed packed plane, okay. If it is an FCC type of a structure in one-on-one plane, this will all might have been the grey colored atoms, okay, then it might have been FCC. And in this, if an atom on the next plane, if it is moved from here to this position in an FCC, that creates a perfect atomic site position. That is, or from here to here is the lattice translation vector, or from here to here or here to here are the three close packed directions in FCC, correct? But here if you see from here to here, if I go, it goes from one atom to another position which is a different type of an atom, okay? So that's not possible. So how do we define a perfect dislocation? Perfect dislocation is the one where the distance which we move is a lattice translation vector in the lattice. So in an ordered lattice, in this the lattice translation vector will be from here to here if we move, or from here to here it is the same distance. That is equivalent to twice half 1 by 2 1 bar 0. That is one thing which we have looked at it. And another close packed direction is this one. In this direction if I look at it, from here to here we have to move. That means that in this 4 times the lattice translation vector of the ordered lattice has to be moved. 4 times the lattice translation vector of the disordered lattice we have to move to generate. That means that the perfect translation vector should have 4 times this value, correct? Similarly, a direction if we come from here to here also 4 times. So that means that in one direction a dislocation with 1 bar 0 is good enough. In other 2 directions dislocation with 2 0 1 bar 1, okay, type of dislocation is necessary to maintain the order in the lattice and the but dislocations of this type, how does the self energy go of a dislocation? It is 4 b squared. That means that the self energy will increase. Instead what happens, so these types of dislocations are normally called as super dislocations. So if this dislocation splits, because since the precipitate volume fraction is very small and most of the dislocations are generated in the matrix, 2 matrix dislocations with the same Borges vector if they pass through, that is equivalent to a superlattice dislocation with an antiphase boundary in between them. And if you look at the self energy of the dislocations, it will always be less here for all these. So in short it means that in this specific direction, okay, if you observe in the TEM, you should see pairs of dislocations, and in these directions, suppose the dislocations have moved, we should have 4 dislocations together. In a matrix which contains all the variants, different variants are oriented in different way, then we should in fact see 4 pairs, groups of 4 types of dislocations. So how many dislocations are necessary? Generally we say that the material is ordered if we see pairs of dislocation. That is not correct. That is only for particular phases it is valid. For all other phases it is decided by crystallography. If you look at the close packed plane, then we get that information how many dislocations are required. In this case 4 groups of 4 dislocations have to pass through to completely restore order in the. In between we will have some antiphase boundaries will come in the sample. Okay, is it clear? This is what the crystallography is as far as perfect dislocation is concerned. But if you look from here, this the minority atom is here, if it moves from here to this position, because this is an atom which is sitting on the next layer, we are considering only that minority atom. If it moves from here, what is the situation? It is in a position as far as the first nearest neighbors are considered identical. But as far as the crystal structure is concerned, a fault has been created. So these type of faults are called as geometrical stacking faults. That means that they maintain that order in the lattice. You understand that? Whereas suppose I move from here to this position, what happens? Or from here to this position. Now the nearest neighbors, if you see, with respect to this position, these two are one particular type, it is a different type. So that has a, since another unlike neighbor atom comes into the picture, okay, that can create an APB also, and these types of faults which are generated are called as complex stacking faults. So that is what it is being mentioned. This is geometric stacking fault, this creates complex striking fault. In this particular alloy system, if I move this atom from here, comes up to this position also, it will create a geometric striking fault. And from here if I move it, this has a threefold symmetry now it maintains. So all of them, if it is whether 4C delta, 4 delta C or 4 delta A, 4 delta B, all of them will create geometric striking fault. So now we have a fair picture of what all types of dislocations which are possible. Once we have identified the closed fault plane, we can expect various types of these dislocations in the alloy when it is deformed, correct? So this information from the crystallography we can get it before we look at the sample in the microstructure. Then we should know what to look for and how to identify. You understand? Then another aspect is that if on every layer, okay, a partial of this type moves creating a striking fault, that will create a true twin in the lattice. A twin will be created in the lattice, and if it moves on every alternate layer in the stacking sequence, then it creates the equilibrium phase. Okay, these are all the things which can happen in this alloy system. So this is all this information we get it from a crystallography. Okay, we do when we do heat treatment. This is exactly what happens. So understanding crystallography tells us about what is the mechanism by which these transformations are occurring, or the mechanism by which the deformation is occurring in the material. That information we can obtain first from crystallography. Because when we work on FCC, we know all the things. If we work on a system which is tetragonal or not, then we have to work out all these things before we go into the microscope, or when you start doing the computation, right? And that is what essentially is being shown here in this particular one, how the movement of a partial, okay, this is on 1/0 plane for the same structure, how it is generating that is every layer when this one partial is moving this atom like this sequentially. Now you can see that this structure and this structure across this plane is a mirror symmetry of each other. So it creates a twin, and if you look at it here also, ordering is there, the same type of ordering which you see here also. So it's an ordered lattice also. Okay, the same, yes. No, what I am talking about is how we can consider twinning. Okay, that is, this is an ordered layer. Okay, the next atom position should come here. Okay, if, and you know that stacking fault happen by movement of a partial A by 6 112 direction. A by 6 112 will be moving an atom from here to here. Okay, if I make a partial like this move in this direction, not only all the atoms in this layer is shifted, all the atoms above the layer are also shifted, correct? Whenever a dislocation moves, like okay, if a dislocation moves in this plane, what will be the net result of it? Finally, when we look at it, all the layers above have been shifted. Is it not? It's not that that layer which is shifting. All the atoms which is above the slip plane, they are getting shifted. Now, if in this next layer after that has happened, again another partial comes, that will be shifting the atoms from here, okay, by, so all the layers will be like this. When we give shift to each of the atom positions like this, then this is the sort of a structure which we generated. Okay, this is by overlapping stacking faults, one on top of the other. Now if we look across these two are related by a mirror reflection. So whenever the structures are related by mirror reflection, okay, we call them as twin. But if you look at the unit cell orientation here and the unit cell orientation there are different, but it's the same crystal structure. Okay, there is any structure which is related by a symmetry relation, any of the symmetry related to the crystal structure, then we say that it is twin related. That's how crystallographically twinning is defined. Okay. No, it need not be from striking boundary. It can be from APB also. Even APB can generate. Antiphase boundaries also can generate. That is why when they call it as, when I call this as 3 variants which it can come here to here, they can be by antiphase boundary we can generate. Okay. Which one? No, what happens is in an ordered lattice, we will always have stacking fault also can happen, or it can happen by antiphase boundaries. What is essentially antiphase boundary? If you take a disordered lattice, it has got a maximum symmetry, correct? When it orders, the symmetry of the lattice comes down. That is, if you take a cubic system, if it gets ordered, it goes into a tetragonal system. That means tetragonal system will have only a 1 4-fold symmetry, it has lost a 3-fold symmetry, correct? Some symmetry element is lost. Whichever symmetry, crystallographic consideration, a symmetry element which has been lost during the transformation process appears as a defect in the ordered lattice. You understand that? That defect could be either appear as a ordered variant that's create as a domain boundary, or it can come as a antiphase boundary. If it is just one antiphase boundary, it is only shifting the crystal structure from one to the other but same orientation. If they happen over a sequence of layers, that may in fact rotate the crystal structure. Then we say that it's a domain or an ordered variant. You understand that? That is how these variants come. So this is how twins are formed in the material. Is it clear? And this plane is essentially called as a composition plane or a coherent twin plane. Okay. Now, having understood this deformation, what all types of modes in which a deformation can, possible modes in which this material, these precipitates can deform, let us look at the microstructure of the sample. That is not the way we do in an experiment, but having done that, now we can go this way. Okay, that is how I am explaining. And the sample which has been aged for a very short time, even the precipitates cannot be resolved, where the equilibrium, not the equilibrium, the metastable strengthening phase has formed. Now, if you see here, there is a group of 4 dislocations, there is a group of 4 dislocations which you can see, correct? Here you see that 1, 2, 3, 4, here 1, 2, 3, 4. Afterwards, here also is there, then afterwards it gets reduced. There is a reason for that. That I will come to later. Okay. Essentially, what you can see is that in this particular alloy system, groups of 4 dislocations are passing through, which are bunched together like this. Otherwise, we see randomly in a disordered material. That is not the way it happens in an ordered alloy. Okay. And when the precipitate size is very large, because these are all deformed to close to about only 1% deformation, plastic deformation. If you see here, this particular one, I do not know whether you are able to see it. This is one dislocation, this is another dislocation. This dislocation, as it has entered, has split into a partial. Only the partials could be seen in weak beam. Okay. You can see that there is a mechanism, there is a slight change. Here, perfect dislocations, groups of perfect dislocations of the matrix pass through. There the perfect dislocations have split into partials. Okay. Now, when I look at the sample which has been deformed to 15 to 20%. Now, where the precipitate size is very small, still you can see only single dislocations, mostly like a dislocation structure, it's a tangling of dislocations and all. In this particular case where precipitates are there, I can see that this sort of twins could be seen, okay, and the precipitates does not appear to be continuous as we have seen. Some places the precipitates are, you can see some lines in between, okay, look at twins. And as I mentioned in the last class or the earlier class, how to identify the twins, okay. Now you can see that there is a twin reflections is there. This is the twinning plane across which all these reflections are getting mirror image of the 1-on-1 diffraction pattern is occurring. This is the way we can identify it. In addition to it, in fact, this reflection also gets reflected to this one, which is an indication that the order is being maintained in the twin lattice also. That is why we call these twins as true twins. If the order of the lattice is not maintained, we call them as pseudo twins. Okay. So essentially now the mechanism in this alloy system when the precipitates are very small is essentially groups of perfect dislocations which are passing through. Okay. When the precipitate size is large, it is not normally what we expect in most of the cases we will say that when the precipitates become large, it is essentially the looping which forms. Here we do not see looping, here a twinning forms. The reason is that as soon as the dislocation comes and touches the particle, since the fault energy of the precipitate is very small, it is splitting into a partial. Okay, that is what is. So the general concept which we tell that from mechanism changes as the particle size increases from shearing to twinning, shearing to looping is valid only for materials where the precipitate stacking fault energy of the precipitate is very high. When the stacking fault energy is very small, okay, instead a twinning is the mechanism which forms. Okay. Then these are all the expressions which are used to find out. This is for groups of dislocations. This is the formula which one can use it to find out what will be the critical result shear stress for twinning. This you can see from any book. If 4 dislocations are there, this value will change from 2 to 4. That is what essentially it happens. Okay. And then Oravan looping takes place. This is what the critical stress. Okay. This is A is the aspect ratio because it is an ellipsoidal precipitate. Okay. The radius to the thickness, there is a variation. So that is what is taken into consideration. And this is a formula which we derived for with respect to an applied stress. If this is the twinning stress which is going to be there, okay, how it is related to a twinning stress, the way. Okay. Then what we did, this is for twinning. Suppose twinning forms in the material, what will be the critical twinning stress we know for a nuclei to generate, and that basis with respect to how it is related to a particle size and the applied stress, are the critical result shear stress for twinning which we can find out. Now, what I am plotting, it is for different aspect ratios which correspond to aspect ratios which I had seen during the full particle size. Okay. The shearing of the particle, how the critical result shear stress will increase with particle size. These are for all done for room temperature. Then for looping to occur, it is essentially 1 by R. Okay. Here it is 1 by root R. That is how it changes for twinning. Now if we see it, for all particle sizes, the stress, critical stress which is required for twinning is always smaller than the stress which is required for looping to take place. Okay. This also confirms that why we are not seeing looping in this particular system. You understand that? Okay. And that is what you can see, that when the particle size are fine where shearing is occurring, this is how the perfect dislocation and here twins. Then we have looked at the what all the types of stresses interactions, and I am not going into all those details here. Okay. Volume fraction remains the same. When you age a sample, okay, okay, once the nuclei has formed, okay, aging condition, when we say that underaging is where the particle, the nuclei grows, okay. At a peak aged condition, when you say peak hardness, the full volume fraction has come. Yeah, the full dotted line is essentially should correspond to that, okay. And then beyond that, actually there will be small changes will be there in that. This is with respect to a mechanism I am looking at it, okay. As far as the volume fraction is concerned, these two need not be the same. So the volume fraction, as the nuclei is forming and the nuclei starts growing, okay, once the critical size of the nuclei has reached, all of them are going only in direction, they do not dissolve. When do they dissolve? During coarsening regime, the fine precipitates dissolve and the large precipitates grow at the expense of them, and that is we called as the coarsening regime. There the volume fraction remains the same, the number density comes down. That is, in the growth regime, the number density in principle should remain that same, but the size should increase. You understand that? That is how it comes. Clear? Okay. So when this was proposed, okay, this was published in I think 88 or in Acta Metallurgica. Afterwards, in another alloy system, whether it's a universal phenomenon which is occurring or not, from a group from University of Cincinnati, okay, they did that work on Haynes 242 alloy, which is a corrosion resistant alloy. There also this Ni2CrMO precipitates form, which has a very low stacking fault energy. This has got an orthorhombic structure, okay, and it has an ellipsoidal morphology. When they studied this, exactly the same mechanism what we have obtained, they have observed the same. That is, as the precipitates become very large, the work hardening rate comes down. You know that whenever dislocations are there, dislocation interaction is very prominent, okay, the work hardening rate will have a value which is large. You know what is the characteristic of a twin? The stress which is required for twin to form is very high, but once a twin is nucleated, if it does not see any obstacle, it will go from one, just tip, it will go through and reach the other end of the grain boundary. Okay. So when such a process happens, in such a situation, the work hardening value will come down. Okay. But afterwards it goes up because intersecting twins will come, that is a different phenomenon. Twinning travels very fast, because you are applying a stress also. Na? Very little stress is required to make the twin propagate, but the stress which is required for twin to be nucleated is very high. Okay. So on this basis we concluded that in an ordered precipitate, depending upon whether the antiphase boundary energy is high or that's whether the stacking fault energy is high or low. If the stacking fault energy is high, essentially the mechanism will change from shearing to looping, and if the stacking fault energy is low, it goes from shearing to twinning. This has been seen in many other alloy systems later. Okay. So all these things precipitate. Okay. Matrix also could have low stacking fault energy, it can happen always. Okay. Because here we are talking with respect to precipitates which are formed in a matrix. Matrix could have some low stacking fault. Here also matrix has, generally many of the nickel based alloys have got intermediate stacking fault energy. It is not like aluminium, it is not a very high stacking fault energy material. Okay. Is it clear? Okay. Then in another student's thesis, that was done at room temperature in my thesis. Afterwards we looked at high temperatures. If you do that, whether the same phenomena occurs. Here also we could see that these are all the twins which happen. When we image with the superlattice reflection of the precipitates, you can see that some regions where the precipitates now actually it has been serrated, right. That is because some regions have twinned. So when we image with the precipitate orientation, those have different orientations, they don't appear bright in contrast, that is why. And in this one, if I see it, this is the twin plane. Here not only the superlattice reflection, also a mirror image of it forms. So that is why this is called as a true twin, as I explained. And in fact, in his thesis, what we did was that we looked at 3 different microstructures. One is a solution treated sample where no precipitates are there, which has been deformed at different temperatures. Then another is one which is aged with only this gamma double plane precipitates which form. Then another is which is the equilibrium phase which it forms, okay, which are coarsely distributed, the volume fraction is small. Then when we look at it here, the solution treated sample up to 600 degrees centigrade, the value of N is very high. Then at 650 and 700 when we go, the value comes down. If you look at that sample, already large size gamma double plane precipitates have formed, because we are doing the test at a high temperature. At that temperature itself when we do, because of the stress itself, accelerated course formation of the precipitation has taken place, that is why it has come down. Okay. And you can see that all the dislocations here are already split into partials when we look at it, right. And in this particular case also, if you see it, always that the value of N is very small, and you can see that it is essentially the twins which are forming in this material. In the where the equilibrium phase forms which are needle shaped. Here if we look at it, in this particular case, it looks very similar to that of a solution treated sample structure. Okay, essentially dislocation tangles could be seen. Here also the value of n is very high. In fact, this value of n could also be related if you know the microstructure, what sort of mechanism which occurs in the material, sort of gross mechanisms which we are talking about, correct? Then the next question which came is that these twins which they form, are they stable at high temperatures or whether they transform? Okay. For which what we did was that after this sample has been deformed at room temperature with large particle sizes, then we aged them at different temperatures. Okay. Another sample which has undergone the same identical treatment but which has not seen the deformation, they were also both were given the same heat treatment. Now when we look at it, I could see that at 650 for 168 hours, essentially the nuclei remains that same, and 700, 800 if I age it, I could immediately see that they transforms to the equilibrium phase. Because why it has happened? The twins have formed, then lot of stacking faults are also there. They are all nuclei. So if you give a sufficient, please rise the temperature, at that temperature the equilibrium phase is able to form by diffusion of the elements to it. And here if you see it, this is the sample which contains only gamma double prime precipitates, okay, because I have not shown the diffraction pattern to prove it. But if you look at the interparticle spacing looks like this, otherwise the interparticle spacing is very coarse. The consequence of this is that when we use this alloy in service, okay, in service some stresses are always going to be there in the material at high temperatures that can deform this material. And if such a thing is going to happen, okay, if the equilibrium phase which forms is very fine and uniformly distributed, the strength will not drop down drastically. That is what one of the conclusions which we can form from this study. And if you look at these twins which are there here, okay, the interface between the twin, this is nothing but, if this one layer on either side if you consider, it is nothing like an ABA type of a structure, which is nothing but the nuclei of the HCP phase. Okay. So essentially what is happening, stacking faults as well as the interface between the twins, both of them are responsible for an accelerated coarsening. And since we have deformed the sample, now we have created plenty of nucleation sites within all the precipitates which are uniformly distributed. So that way we are able to modify when the equilibrium phase forms, okay, their distribution could be modified, that is how the strength could be controlled. In fact, in a alloy of this material, not alloy, that this 709 material which has been used as a turbine disc and which has seen service of about something like 25,000 hours, when it has been seen from up to them, they could exactly notice that the same type of mechanism, that the temperature where is low, gamma double prime precipitates are there, where it has seen the high temperature, already the delta phase has started forming, in between they could see faulting and twinning. Okay. So this gives the satisfaction that what we have studied, it is quite useful to explain the microstructure which is seen in a structure which has seen very long time in service. Okay. Then I will now go to in PE16, mnemonic PE16, which contains very small volume fraction of gamma prime particles. Okay. I looked at the fatigue structure. Okay. Here also the particle sizes have been varied, different particle sizes are chosen. In some particle sizes, it could be shearing which could take place when the particle sizes are fine. When the particle sizes are large, it could be twinning which could, it is not twinning, it could be looping which could take place. Okay. In the deformed sample, you remember that in the morning, Marc told us that how the precipitates change their morphology, that when they are getting sliced. If you have a precipitate which is like this, circular like this, if dislocations pass, okay, along this, it will be essentially the size will be changing like this. Okay. This is what you could see at many places. Here there are here, here, here a slice is being taken out of it because two parallel slip planes, okay, the dislocations are moving. Okay. This is PE16, mnemonic PE16. This contains low volume fraction. So it's much simpler to, for basic mechanisms, it's, look at it. It contains about 10% gamma prime. And in the microstructure, if we look at it, we can see essentially pairs of dislocations could be seen initially. Okay. Then beyond that, you see essentially single dislocation, it appears. Why this happens? Could you tell me why this sort of thing which we see? Initially pairs and after that in the pile up at the back, when the dislocations have cut. It's a shear, this is to do with the particle size. That is, if I see a particle of this particular size, in the slip line I know if this is the distance d. If I know b, d by b will give you how many dislocations should have passed through to separate this into two separate half, correct? Once in the slip plane, it has already separated. When the dislocation passes through the rest of the dislocation, it doesn't see the ordering at all in that slip plane. So it will be essentially like a perfect matrix dislocations will be passing through. Then you will not see the group of dislocations. Okay. No, looking at TEM, you can get all this information. That we have done that. Afterwards, looking at the particle sizes, we could infer and calculate how much will be how many dislocations should have passed through. These are very simple calculations. Yeah. Yeah. Yes. Yes, does happen in fatigue. This is reality. In fact, the precipitates get completely dissolved. I will show you in this alloy. We have seen that. Hmm? In principle, the dislocation need not stay together. Yeah. What is happening is that we are not seeing the precipitates. These are not over one particle. This is essentially, that is why if you look at many of these, you can have that the separation is not that same. There will be a variation in separation depending upon how they are there. Within the particle, the separation will be small. Below, beyond that, it is essentially the equilibrium distance which they will try to maintain between them, which is decided by the elastic considerations.
Is it a pile-up?
No, pile-up effect is also going to be there. From the back, the dislocations which are coming, they are also going to apply the stress. Okay. And because the case which we look at it is as one we consider it, but dislocations are uniformly distributed. They are not dislocated. Precipitates are uniformly spatially distributed randomly, and the dislocation has a long length. As it passes through, the equilibrium structure which we see is because they are passing through many dislocations. Some regions they have come out of the particle, they are not within the particle. Some regions they are within the particle, correct? Here you can see these particles which are sliced into half, correct? In this particular one, okay. In this particular one, if you see it, this is a microstructure where the number of cycles has been increased. Other than the particles which has been sliced in this direction, okay, in this particular direction also, cross-slip direction also, the particles are getting sheared. Okay, many multiple slip systems when they start acting, and what is the effect of this when they operate like this? We can think of that initially dislocations are moving one slip plane, then in another parallel slip plane they remove it, okay, like this it will be happening, and then in another slip system which activates, it will be cutting these slices into small sections, and finally this is what it is going to happen, okay. And if the number of cycles are more, the size becomes so small that they can dissolve, be smaller than the nuclear size. And in fact, similar to that, what is happening now, if you see it, where the number of cycles is large, you see regions where precipitates could not be seen, correct? This region could mean that it is below the resolvable size, but the particles are there. That's one possibility, or the precipitate itself has dissolved. These are all the two possibilities which occurs in this case. To understand this, what we did was that we took the samples where it appears as if within the band, shear bands, the precipitates have dissolved. Okay. Then we aged for a very short period of time at high temperature. So then what happens, the large particles also grow, these smaller ones also from that size they will start growing. That is precisely what it happened, and we could see that very fine particles could be seen within this band reappearing. This is an indication that still it does not tell us that whether the precipitates are, what was the initial size. So what did we do? We tried to study the kinetics of this as a function of time. Okay. This is what essentially is being plotted, and then try to see to 0 time where it meets, okay, whether it is below the critical size or not. On this basis, we could conclude that in some microstructures where the precipitate size are fine, and that has taken a large cycle, the precipitates have completely dissolved. In one where the size is large, still we are not able to see it, they are remaining there. This was also published in Actamen. Okay. So we just put up a mechanism that this is how it will be appearing schematically. Understand that. There are in many systems like aluminum lithium alloy system where lithium diffuses fast. The lithium comes here and the particles which are very close to these bands, they grow to a large size preferentially. That has been observed. Okay. So essentially shearing, this is what the mechanism which leads to when Orban looping takes place, okay, when we load and unload the sample, then what's going to happen is that essentially since looping forms around the precipitates, okay, and the dislocations will be cross-slipping also, and because of that you find uniform homogeneous distribution of the dislocations you see. The type of bands where the precipitates have completely disappeared, they don't appear for large particles. We have not seen that. Though some bands could be seen, but, and you can see that here this is loops could be seen around a particle, and there is another loop which is dislocation which is coming. Okay. Could see clearly. But I had some microstructures which I could not get it, where over 2 or 3 dislocations, now each dislocation has got one loop around it. There is another dislocation which has formed around 3 particles together, but I am not able to get that microstructure. Okay. From here I will go to some study which we have done on serrated yielding in titanium alloy. The problem of serrated yielding is a phenomena which is very important for many materials, because we know that when DSC prevails, there is conflicting reports that in some cases the improvement in mechanical properties, some cases there is a decrease in mechanical property, but whatever be the case, we should know what is it which is really happening. In most of the cases, steels or nickel based superalloys, they contain solutes which are substitutional solutes or interstitial solutes. Both these solutes, okay, could give rise to serrated yielding. What is serrated yielding? As the dislocation comes and they are stopped at obstacles, the solutes can come and form an atmosphere around them. When they form an atmosphere around them, the dislocation to move, okay, higher stress which will be required, and once it has broken that stress, broken the atmosphere and comes out of it, it will move very fast till it sees the next obstacle and where it is getting caught. So essentially this will give rise to, on the stress strain plot, we will have like this sort of serrations which appear, right? This is what the net effect which we see. The question which comes is that if it is due to interstitial elements or around the dislocation core, small region they form, how to identify them? When they form up large precipitates, we can identify. Especially in many cases, it is essentially carbon, nitrogen or oxygen. Seeing them in a microscope as an oxide or this one will be possible. When they just form a solute atmosphere, it is going to be very difficult. There are 2 techniques which can be used. One technique is an atom probe, where we are able to identify how every atom is distributed. But the problem there is that getting a dislocation with an atmosphere in that sample is going to be a Herculean task. We do not know what it happens. The other technique which one can employ is energy filtered electron microscope. You have heard of energy filtered transmission electron microscope? Any of you? No? Okay. When the electron beam passes through the sample, okay, what do we assume? That essentially diffraction, when it takes place, it is essentially an elastic scattering. There is no change in the energy of the electrons when it gets scattered. But in principle, what will happen, what is spectroscopy technique depends upon. Suppose this electron enters, some electron, okay, when it meets an atom, it can lose some part of the energy, correct, to generate a characteristic X-ray. Then what would have happened to that electron? The corresponding to that energy which is required to generate the character, to excite the K level, that much energy it has lost, or L level, and that much less energy will be the electron which it will have. So these electrons also, if you look at it when they come out of the sample surface, if you do an energy analysis of these electrons, we will find that not that uniformly they have lost electrons, suddenly you find that some electrons have got lost of electrons, some specific amount of energy and they have come out. Okay. This how we can identify is that using a magnetic sector analyzer, we can change the direction of these electrons separately. So in a microscope column, a magnetic analyzer is being introduced. What it does is that the electron, as it comes out of the sample surface, it makes it pass through an analyzer, it comes like this. So this is called as an omega filter. The path changes like this. So various electrons with different energies, depending upon the energy, some will reach here, some will be getting scattered. So only electron, depending upon the magnetic field which we apply, only electron with a specific energy will come out. And this electron, when it passes through the other lens, it forms an image. Now we can form image in the microscope with electrons which have lost specific amount of energy. This is called as a electron energy loss. This is called as a energy filtered transmission electron microscope. In principle, it should, but in practice, it is difficult. Okay, there are many reasons for that. The technique as such should, technically it should do. That's what I said. Okay. Now what we have done it is that this is a gamma titanium alloy, okay, which contains, other than titanium and aluminum, some carbon, nitrogen, oxygen are as impurities. No, not gamma titanium, it is titanium 6Al4V. That doesn't matter. Okay. What is essentially important is that oxygen concentration is the highest in this alloy from chemical composition which has seen. Carbon is the less, nitrogen is intermediate. Okay. So using this technique, we can image the sample. Okay. Initial energy we know, the one which has lost an energy corresponding to that of carbon. Then we could see that a sample which has been tested at 300 degrees centigrade tensile tested in this orientation, we could see that on some of the boundaries as well as some dislocations, there is a faint white contrast could be seen, which suggests that there is an atmosphere which has formed around them. Okay, because the resolution in this system is now almost close to 2 or 3 nanometer, 2 or 3 amps, or maybe 10 angstrom of that order. So generally an atmosphere around the dislocation could be identified using this. And this technique is especially sensitive, energy filtered, for low Z elements. Okay. Now when we see for nitrogen or oxygen, we don't see any of them. This is, we can give a color so that we can see them very clearly. Okay, this is what it happens. The same thing which we have done it in another sample which has been deformed at 450 degrees centigrade tensile tested sample. Okay. Here also you could see that on the boundary where contains dislocations which are there, this preferentially, okay, this carbon has gone, in this case nitrogen has gone, oxygen has never gone. So we feel that essentially the carbon and oxygen which is responsible for formation of atmosphere around this alloy system and giving rise to serrated yielding. in order to find out whether this sort of a segregation has occurred due to a heat treatment itself. That could also happen, the sample we have solution treated and all, for which what we did is a sample which was tested at room temperature, where preferentially we looked at that microstructure, we find that neither carbon, oxygen nor nitrogen has segregated to these dislocations. From this we could conclude that whatever the segregation which we see has happened during deformation, which is responsible for the serrated flow. That is how we have confirmed it. Okay. So I think almost about 1 hour I have taken. So with 3 cases in a tensile deformation, one in the case of a serrated yielding and in the case of a fatigue, just try to explain how one could get gross information, but other information about if I go into a detailed dislocation structure, some are there, it will be too complicated to understand. I thought general information is much better to give that, so that it is easy for you to comprehend. Okay. Now you can understand what all things which can be done with a microscope. It is just a few examples. Okay. These are all the books which I use it for teaching microscopy and crystal structures. One is Solid State Physics by Ashcroft and Mermin, it's a very good book. Then Kittel, electron microscopy, this D.B. Williams and Carter, and Basics of Crystallography and Christopher Hammond, and Transmission Electron Diffraction of Materials, Fultz and Jim Covey. These books are quite good. Then day before yesterday, people were asking about books on some of this crystallography, point group, space group symmetry and all this. These are all the books. Introduction to Crystallography by Martin Berger. This is very good book. Basics of Crystallography, here also it is explained. Then Crystallography and Crystal Defects. This explains, it's a very nice book. I think I will all tell you that to have a preliminary understanding, one should read this book. How different types of crystals form, what are the types of dislocations which we could generate, modes in which it could be deformed. Okay, then about morphostatic transformation, glide, then about the deformation in a tensorial notation, general deformation, and then from that when we consider a specific glide planes, how to, in vector notation and tensor notation, how we treat it, that is the way it is done. This one can read this book. Then this is a book which gives about all the 14 crystal structures, very simple book. This is a book which crystallography and crystal chemistry, it's a little bit advanced. Okay. Then in some cases you read even Introduction to Solids. Ashcroft book also gives all the various crystallography and point group and space group symmetry, that is explained very nicely. Okay. Thank you very much for patient hearing. I will stop here now. If you have any questions, please do ask.
Oxygen.
Yeah.
Carbon and oxygen segregate to the dislocations, right? Which gives serrated yielding.
Yeah, correct.
But then you show that appears.
Yeah, there are two things which happen. No, the two things which happen is that there are some boundaries which will contain dislocations where it could segregate even during heat treatment, but at very high temperatures interstitial elements move very fast, they may not form an atmosphere. This can happen only at lower temperatures. So normally we quench the sample, so the chance of that occurring is very small, that is why we do not see them. But at room temperature, that is just to make sure that whether it has happened or not, when at room temperature when we deform, the dislocations are formed. So we wanted to verify what is the temperature, but at room temperature we do not see any serrated yielding also. So when we look at the microstructure, we do not find any segregation of these elements to the dislocation. And at slightly elevated temperature where we see the serrated yielding, we could notice that there is a segregation which is occurring. Okay. This is published in Material Science and Engineering. I think in the last 4 or 5 years only people have started using energy filtered microscope to look atmosphere around dislocations. I always find that has always been troubling me, that when we wanted to study this phenomenon, unless we are able to identify what is the atmosphere which it forms, because most of the theories telling that this is what might have come, and indirectly in mechanical metallurgy you look at the activation energy, which sometimes gives values which are meaningless. Every element could have come, that sort of a thing, then you tell that this is the element which has come. So I feel that the best method is that if we can, using some experimental technique, we can observe atmospheres. Yes?
These elements are affinity to dislocations.
Yeah. No, affinity to not dislocation essentially is what happens to a dislocation. Dislocation has got a strain field associated with it, correct? When you have a strain field which is associated with it, these are all interstitial elements. Okay, depending upon the size, they will come either onto a compressive side or the tensile side of it. That's how it happens. That's how the affinity comes into the picture. This you might have studied in basic dislocation theory. Okay. Yes.
And can we simple time energy filtering is an attachment to the temp?
No. It is a microscope comes like this. In India, as of now, there are two places where it is there. One is there in IIT Kalpakam. Another, this I did it in IIT Kalpakam. When they got it, I knew that I told them I have a problem to be studied. Okay. Then another is in NML Jamshedpur. They have got a 300 kV energy filtered microscope. These are all the two places in India they have this microscope. Okay. Yes. Essentially, this atmosphere, earlier theory was telling that this atmosphere forms as the dislocation moves with a particular velocity and the solute also moves and they come and join together. But the later, Curtin is one person who has done a lot of work on looking at this. And the present, this one is that you have a forest of dislocations are there. As the glide dislocation moves, they are stopped at the forest of dislocations. During that time, these solutes come and get attached to it. That's one theory. The another thing which they have said is that this forest dislocation is also stationary. So Curtin's argument is that the solutes could have come and formed on the forest dislocation, as well as and when these dislocations are stopped, from the matrix, the solute will come and form an atmosphere. Then through pipe diffusion from the core of the dislocation, from the forest dislocation also they could form an atmosphere. That is the basis on which they have developed the theory. But I find that that theory, I consider it as the most reasonable, which takes all mechanisms into account. Okay. So what is the extent to which they will form depend upon what is the resident time at which the dislocation has been stopped by the forest dislocation, correct? And that also depends upon the strength of the forest dislocation, because depending upon the orientation, what is the type, it will have different strengths. Yeah, correct. They have just close to it, correct. Okay. Sorry. Any other question? Yes. Yeah. Yes. No, in fact, many of the phase transformations from FCC to HCP or HCP to FCC is essentially taking place through defects. In fact, many of the alloy systems, the phase transformation, many alloy system crystal structures, if you consider, by introducing an antiphase boundary, we can go from one structure. Like I showed that in L12, along particular 110, if you introduce an antiphase boundary, we can create an orthorhombic structure, correct? Not orthorhombic, tetragonal structure. From the tetragonal structure, by introducing a stacking fault, we can generate the crystal structure of the body-centered orthorhombic structure. Similarly, there are many systems are there where from creating antiphase boundary, we can go from tetragonal to orthorhombic structure. All these things are possible, they do occur in most of the ordered systems. That's very common. Okay. In fact, we have done a study on looking at deformation behavior of ordered nickel 3 vanadium and nickel 2 vanadium. That's a eutectide transformation. In nickel 3 vanadium, along 1 to 0 plane, if we introduce an antiphase boundary, that is nothing but of Ni2V composition, which is essentially orthorhombic structure. Okay, crystallography you understood because imagining is difficult unless you look at the crystal structure, but that sort of a transformation occurs. I just showed that in the last class or before that, but I didn't go into a detail because I thought that was not important. Phase transformation is not an important thing which we have to consider here. Okay.